Hey everyone, and welcome back to All About AI Tech. Today, we're diving deep into a critical area of cybersecurity, side-channel attacks. These attacks are sneaky. They don't directly target the cryptographic algorithm itself, but rather exploit unintended information leakage from the system's physical implementation, like it's running on a particular hardware, or it may be based on some specific software, it might be based on the type of communication, or it might simply be related to the operating state, such as the amount of memory occupied, CPU utilization, power consumption, or timing of operations. This leaked data may be used to break the ciphers used. Think of it like this. You have a super strong lock on your vault, but the sound the lock makes as it turns could reveal how to pick it, or the subtle vibrations may reveal information about the key. That's essentially what a side-channel attack does, and it's not something your typical user has a chance of even thinking of. These attacks are a major concern, especially with increasingly sophisticated algorithms and the growing demands for real-time processing. These attacks pose a significant threat in systems using cryptographic algorithms, which underpin much of our digital communication today. Just think about how many devices around you are constantly sending and receiving data, with algorithms ensuring their confidentiality and integrity. Side-channel attacks are a massive challenge that requires new ways of thinking about how to design protective algorithms and maintain security. We need innovative solutions, and that's where AI comes in. Now, let's talk about one of the game-changing tools being used to combat side-channel attacks. Wasserstein Generative Adversarial Networks with Gradient Penalty, WGAN-GP. This may sound super geeky at first, but here are the fundamental ideas. First, adversarial networks. In machine learning, adversarial networks involve two separate models. In essence, the first, the generator, generates sample data similar to the target data, and the second, the discriminator, tries to distinguish between the real data and the data generated. The two interact, and by learning each other's parameters, they continuously improve, getting closer and closer to each other. The WGAN component stands for Wasserstein GAN, a methodology to reduce instability issues in generative models. The gradient penalty method attempts to reduce the gradient of the generated data to 1, which aims to improve the quality and reduce variability of the generated samples. The key here is that this algorithm will allow us to generate high-quality synthetic data that mimics real-world scenarios, and that effectively covers the data space in a way that traditional methods are not able to do. It's especially efficient when data may not be available, or generating real data is expensive, difficult, or time-consuming. WGAN-GP is used by creating realistic synthetic traces of cryptographic implementation, for example the memory occupied, time taken, or power consumed, which can then be used to develop more resilient protocols better able to withstand attacks. This is where the generative power of these AI methods really shines through, creating training data that is both realistic and scalable. This is an ingenious improvement that would not be achievable using the traditional techniques. Next, we'll explore the power of genetic algorithms, GAs, another important AI technique in this context. GAs draw inspiration from biological evolution. Their fundamental workflow is similar in spirit to that of an EA. Starting with a random population of potential solutions, the algorithm evaluates each of these solutions against a target metric, here, strength against attacks. Good solutions, the fittest, are selected to seed the next generation and modified through processes of mutation and crossover, similar to what happens during reproduction and mutation in nature, all of which increase the diversity among the generated solutions. Using such a randomized evolutionary approach, algorithms can overcome some of the limitations of traditional optimization methods. In particular, GAs are quite powerful when applied to problems that have many local optima and/or don't have neat analytical mathematical solutions. Unlike many traditional methods, they do not have assumptions of differentiability, continuity, or similar conditions. In this case, GAs are used to optimize the parameters and configuration of the cryptographic protocols generated with WGAN-GP. GA iteratively refines these configurations over numerous generations to discover a set of parameters that optimize the balance between security, efficiency, and side-channel resistance. This represents a dynamic adaptive strategy to continuously improve cryptographic protocols that would not even be thinkable without taking advantage of these revolutionary advances in artificial intelligence. This is where the synergy with WGAN-GP is particularly strong, as this process produces and refines solutions over many generations, which in turn produces highly effective and useful results in improving the security and efficiency of cryptographic systems. Let's now compare this powerful hybrid AI-driven cryptographic approach with RSA, a classical public key cryptosystem and widely used in secure communications. RSA relies on the computational difficulty of factoring large prime numbers to provide a strong theoretical security. However, RSA is indeed known to be vulnerable to side-channel attacks, such as those based on timing differences or power consumption. Our hybrid AI-driven framework, in contrast, stands out for its increased ability to withstand such vulnerabilities. It leverages the synthetic traces generated by WGAN-GP for robust training and employs GAs to efficiently tune the cryptographic protocol's parameters. As a result, we obtain not only security but also high efficiency and adaptability. Consider efficiency. RSA can be relatively slow, particularly given larger key sizes. This can be a problem for real-time applications, whereas the proposed framework uses optimized symmetric ciphers. Adaptability is another key differentiator. Unlike RSA's static key management, our framework integrates dynamic methods such as periodic key rotation and renewal. This approach mitigates the risks associated with key reuse, a well-known weakness in cryptography, and enhances the overall security profile and adaptive security solutions for cloud computing. Overall, the experiments reveal that the novel hybrid approach markedly enhances resilience against side-channel attacks while delivering higher efficiency and adaptability than traditional methods such as RSA, making it highly suitable for current and future security needs, particularly in contexts such as cloud computing and IoT. The hybrid framework's dynamic key management is particularly relevant in securing cloud environments against evolving threats. Finally, let's look at some specific applications. This hybrid AI-driven framework shows great potential across a variety of sectors. First, consider the Internet of Things, IoT, and embedded systems. The use of resource-constrained devices in IoT requires algorithms that are both lightweight and highly secure. Traditional algorithms like RSA just will not cut it in many cases, and they lack the efficiency needed for real-time applications. Our hybrid framework is ideally suited for these scenarios, as it offers both high security and resource efficiency. Consider real-time applications. Systems like secure streaming and encrypted video calls need very quick response times, where latency due to computationally expensive methods is simply not acceptable. Our approach can boost speed and minimize latency to satisfy the requirements needed. Similarly, our framework strengthens security when dealing with hardware security, and its ability to defend particularly against side-channel attacks is really valuable because side-channel attacks pose a great threat where attackers may potentially have physical access to the device, such as by monitoring its power consumption or measuring the time it takes to complete operation. Our enhanced side-channel attack evaluation incorporates multiple metrics, capturing a wider range of threats and environmental changes. The incorporation of synthetic data generated by WGAN-GP increases the robustness of evaluations and contributes towards systems better able to withstand attacks. This flexible and adaptable framework can be scaled and adapted in a continuous manner. The improved security and efficiency of the cryptographic protocols makes this a formidable tool for use in any application domain that takes the security, efficiency, and adaptability seriously. Here, we are not limited to theoretical modeling and have demonstrated experimentally that significant improvements are attained in security and efficiency across diverse applications that run on a range of hardware, highlighting the significance of adapting cryptographic methods with AI in meeting the demands of various diverse sectors, including critical infrastructure and secure communications. I hope you found this deep dive into cryptographic optimization using WGAN-GP and genetic algorithms both informative and exciting. We've seen a powerful synergy here between AI and cryptography. By generating a more robust and comprehensive evaluation of side-channel resistance, we have demonstrated in this article the great potential that comes from combining advanced AI and algorithms in the design process of cryptographic systems, especially when applied to solving critical security and efficiency challenges. The development and implementation of these algorithms is important, not only for the development in cryptography, but also for its impact in many related sectors such as IoT, secure cloud communications, and hardware security. As technology advances, new and imaginative solutions will need to be developed that continually adapt to changing security circumstances. We can expect to see increasingly more applications of advanced AI and algorithms, not only in cryptography and its application to these areas, but across many sectors such as finance, healthcare, and energy. This opens exciting opportunities and simultaneously poses new challenges regarding the security of these technologies that must be taken into account. Continuous monitoring of the security and performance of our systems, employing the latest techniques, will therefore remain essential as these new methods mature and as technology evolves.